It's excellent to have Hugo from Daedalean with us today in order to present concretely what a company can be doing, and again, even under the process of certifying. Hugo is an avionics systems engineer with more than 15 years of experience developing avionics system for civil and military certification. At Daedalean, Hugo works on the certification of AI-based application for situational intelligence in the cockpit. Prior to joining Daedalean, Hugo worked at Pilatus Aircraft as an avionics system engineer for 6 years and served before in the Portuguese Air Force for 7 years in various roles, but primarily as an avionics system engineer as well. So he holds a master's degree in electrical engineering, avionics from the Academia da Força Aérea Portuguesa. Okay, thank you, Hugo. The floor is yours.
Thank you very much, Guillaume, for introduction. As you heard from him, I am not a machine learning expert. I'm an avionics systems engineer, but I hope to show you that machine learning certification is indeed possible and give you our use case of it. So I work at Daedalean. We're a 150 people company of very highly motivated and passionate people about aviation and machine learning. So we looked at how can we support aviation? How can we improve safety? We thought, well, why not use computer vision and neural networks to support general aviation in their roles of traffic avoidance, of looking at outside the cockpit and seeing what is there, how can I fly safer? So with that in mind, we came up with a few applications of our technology. We have visual positioning, where we use a downward-facing camera to figure out a lat-long position based on a pre-established map. This is extremely useful, unfortunately, nowadays with GPS-denied airspaces where we see aviation flying. But then we thought about visual traffic detection, where we put cameras facing forward and sideways, and we train neural networks to detect objects flying and alert the crew if there's a potential collision problem. Same type of architecture can be used to detect runways. We just need to train the neural network to detect a different type of object. In this case, a visual landing guidance can provide ILS-like guidance to an aircraft with a runway that is not supported by any kind of infrastructure. We also have potential applications for unmanned drones or any kind of aircraft that needs to find an emergency landing site and avoid damage to people or other structures. So we look at all of these and we thought, okay, so let's apply for an STC. And we have our project with the PilotEye, which is ongoing, where Avidyne is the applicant with the FAA. And this is a concurrent validation with EASA. Project is going well on its way. It's focused on general aviation Part 23 aircraft, using 3 cameras installed on the wings and in front to have a good field of view of the area in front of us. Then we decided, okay, we need to do something ourselves as well, directly with EASA, as we apply for a design organization approval. And so we came up with Illumina Vista, which is basically the same architecture, the same type of design, but for Part 27. So in this case, we're the applicant with EASA, and we're also doing a concurrent validation with the FAA for this, because we want to make sure that the authorities are moving in the same way together. And this is, like I said, same type of approach. We're just using a camera pod with 3 cameras and the same computing platform, just a different display than the PilotEye. So these projects, both of them rely on the same traffic detection technology. And it's basically the cameras capture high resolution images, 6 frames per second. We apply some pre-processing to the images, we crop them into smaller sizes, and we pass them through a convolutional neural network. Now, this neural network is going to be able to detect if there is an object or not in there. But as you know, the prediction of the detection performance of a neural network on a single frame is quite small. So we need to apply other types of post-processing to the result of the neural network, which is going to increase the performance of the system overall and provide a good traffic detection situational awareness system to the pilot. So where is this? So we started quite some time ago with the CODAN reports with EASA. We've done a project with the FAA for a visual landing system, and we're basing our certification means of compliance with the first usable guidance that was released, as you heard from Francois quite some time ago. We have issue paper and CREEs accepted for the PilotEye project, and we're going to use the special conditions released by EASA for the Illumina Vista. We are well on our way to certify these projects, and we are fully confident on being able to do so. As you've heard extensively in the morning and before as well by Francois, the first usable guidance relies on the trustworthiness concept, and it has different building blocks to it. So I want to take some time to talk about one of these building blocks, explainability for development and post-ops explainability. So we have a very high parametric input space. If you think of the outside world, the different combinations of aircraft flying, of different backgrounds, weather events, changes over time, it is just very, very high complex, and it is impossible to capture every single type of image that's going to be input into our system. So one of the key aspects is to properly categorize and characterize the operational domain. So that's the work that goes into the ODD from the first usable guidance. And here I give you just an example of how we established the different operating parameters that affect the performance of our system. So we've mapped them out, and this allows us to have a good relationship between them, understand how they affect the performance of our system, and have a clear idea of the corner cases that may appear. And this then gives us into the objectives of data completeness and data representativeness. So we fly around a lot, we gather data from our users of our experimental systems, and we use all of these images annotated by humans to train our systems. Then we need to make sure that these data sets represent the real scenarios that the aircrafts are using our system are going to fly in. But it is, of course, impossible to expect that the data sets are going to be completely covering the entire possibilities that we can get. And this is where other things like what we've heard in the beginning of using synthetic data, of using different statistical analysis, that is going to come in to make sure that what we have is enough and complete without covering completely the input space. So data recording, this is another objective that is key to the post-ops explainability. It is the certification objectives to support the monitoring of systems in operation and to support accident or incident investigations. But it is also very key, as we all know in the industry working in AI, data is the king. We need data to create new systems that behave better, that perform better, and can do more functions. So it is in everyone's interest that this data recording system works properly. Now, we don't have, as an avionics supplier, we can't rely on a good infrastructure of servers, of collecting data. So it is very important that we understand that we need to record data that is enough to troubleshoot the system, to reconstruct what happened, what led to that event, but also the data we record cannot have bias. So we need to make sure that the requirements that go into our data recording system account for that. Now, continuous safety monitoring. This is based on the data recording that we do. And we need to evaluate what keeps happening once the system is operational. What happens if when we characterized the operational domain, we made mistakes? What happens if now there's quadcopters flying around that are in a much more higher density than before? So these things are going to change the performance of our system, and we need to monitor for this. It is key, and frankly, we done this from the early days of our company. Our data management plan, our data recording system, our data flow is all built to account for this. I'll give you just one example of this. Our early days of the traffic detection system was made using R44 mostly as the object to be tracked. And as you can see, it has a very clear triangular shape that the system in the early days was detecting traffic cones because it had the same system, the same shape. So these types of things, and this was, of course, early days and the clear ability to resolve this, but it is key during operation that we prepare our systems and our processes to account for these types of things. So thank you very much for time being here. It was an honor. Thank you.